Today we're going to take a look at the ring of charge. Imagine you have a metal ring with additional charges added. Just like with the charged rod, we divide this ring into individual point charges. The location of each point charge will have an X component and a Y component. The magnitude will be the constant radius of the ring, while the angle will be changing. Working out a little trig, we see that X is R times the cosine of theta, and Y is R times the sine of theta. So to program our model of the charged ring, we just have to take our code for the charged rod and change the geometry of the point charges. So like we saw in the intro, we're going to be going around in a circle, which means we're going to be changing this value for theta, the angle. So we've got the radius of the ring times cosine of the angle for the X coordinate. We've got the radius of the ring times the sine of the angle for the Y coordinate, and we're going to leave Z fixed at 0. So this ring is going to live in the XY plane. It's going to keep Z fixed. We're going to have 50 points of charge along the ring, and our radius of the ring is going to be 0.1. When we set up our observations, the observation points are going to be in the XZ plane, so we're going to leave Y fixed. Y initially, let's start it out at 0, so we're nice and centered along the ring. And we're going to make the radius of observations, so the distance of the observations from the center of the ring, to be about half as much again of the radius, so 50% more than the radius of the ring. And then our electric field calculation goes the same way. We just go over the list of slices and add up the electric field, and then create the arrow for each of them. So we'll run this with Control 2. So here you've got our ring of charge, and we've got the electric field going around it. You can see it's stronger at the edges of the ring because the observation point is closer to these point charges, whereas it's weaker getting away, near the center of the ring, because we're farther away from the charges, but also because the fields are now canceling with each other. Before, we had lots of field all pointing in this direction. Here we've got an equal amount of field pointing to the left and an equal amount of field pointing to the right, and so the only field components that survive are the ones pointing outward like this. You also notice that all of our electric field vectors fall into a nice plane going around the ring, going perpendicular to the ring like this. Again, because all of the upward and downward components are canceling, because we are centering this ring kind of along the middle of the charged ring. That doesn't happen if we move this Y obs. So let's add another set of observations here. And we're going to move this up a little bit. We're going to move it up to half of the height of, or half the radius of the ring, I should say. So so at this point it's going to be halfway between this set of points and the top of the ring. So what you get in this view is electric fields whose up and down components have not canceled, because we've got more charge over on this side of the observation ring that's got charges pointing upward compared to the charges up here that have fields pointing downward. Again, these are all positive charges, so the electric field is emanating outward from each of them. So you get this sort of overall outward effect, but you're also getting a net upward component to each of these electric fields. Now, of course, the ones in the center here are still pointing directly outward because you've still got the cancellation of the left and right components, but you don't get that in, say, this electric field vector or this electric field vector. Now, of course, we can get the opposite effect if we just go to the other side of the ring. So let's suppose I take our newest addition here, copy and paste, and let's flip this to a negative 0.05. So now we've got a set of observation points along the center of the ring, above the center of the ring, and below the center of the ring. And the observation points below is just giving the mirror image of the points above. Again, because you've got more charges up here, giving you more downward electric field component than you have charges down here, giving you an upward electric field component, which is pretty cool. Let's add just a couple more sets of observation points just to get a complete picture. Let's take this whole thing and copy, Control-C, and paste Control-V. And let's put these all the way up to the top and the bottom of the ring. Get a complete picture here. So here you've got a pretty complete picture of the electric field. You can see that you basically get this kind of fan of electric field vectors with a little bit change in the magnitude. Out here you can definitely see that the magnitude is decreasing along here as you're getting farther away from the charges. Of course, we're not just interested in how the electric field behaves as it goes around the point charges. We also want to get an idea of how the electric field behaves as you get farther away. So for that, we're going to turn to another code. This has the same setup, so we've got the same geometry of charges going around the ring, only this time we're going to set up a graph to take a look at the electric field magnitude versus z. So remember, the ring of charge is arrayed in the xy plane, so we're going to be going out along the z-axis, and we're going to be starting as close to 0 as we can get. Actually, I'm not doing log scale anymore, so I can make this exactly 0. And this has one of my favorite effects in all of intro physics. So here we've got the same ring of charge. Here we've got our electric field vectors. If you zoom in on the center here, you can see you get a teeny tiny electric field vector starting out, and then it starts to grow bigger because in the center, you've got all of these electric field components canceling out with each other because there's no component pointing outward or inward. But as you move out, you get more and more of the components pointing in the same direction as opposed to pointing in opposite directions, so you get less cancellation. But as you get farther away, that 1 over r squared starts to kick in and you get smaller electric field again. What that means is this thing goes from 0 up to a value back down towards 0. So in a rare instance, in an introductory physics problem, you actually get a maximum, and that's actually exactly what we get here in the result. So this is the electric field versus z. We start out at 0, or pretty dang close to it. We end going toward 0, and we end up with this maximum at right about 7% of the radius. And so to me, this is a really cool feature, this maximum, because it's not every day you get a maximum in an introductory level problem. Let's see. Let's try change a few things, see if the location of this maximum changes. So this is at about 7% of the 7% of the radius. I don't think that changes with the total charge, but let's try doubling the total charge. I'm pretty sure it stays in the same spot. Yeah, right about 7%. Yeah, because the total charge is just changing the magnitude of the electric field. It doesn't actually change the geometry of it. So let's go back to this. Let's see how that changes with the radius of the ring. Let's cut this in half. Let's go to 0.05. And so here we get a, let's see, we cut that in half. Ooh, and this gets cut in half. Oh, actually, excuse me, that was at 70%. My ring is of radius 0.1. So here's the actual radius of the ring is 0.1. Actually, well, now it's 0.05. So yes, we're getting about 70% of it. Oh, actually, I probably know exactly what it is. If I go back, if I look it up, I'm sure I'll find out that it's the square root of 2. Yeah, so right there at about, yeah, so 0.7. I'm willing to guess that is right at about square root of 2. Let's see, how would I test that? Or 1 over root 2, excuse me. So if I make this scale, if I make this ring have a width of the square root of 2, then 1 over root 2 of that should be 1. So I should get a maximum right at about 1 now. Oh, look at that. Yep, that maximum occurs. Yep, the maximum occurs at 1 root tooth of the radius of the ring. Let's actually use the new feature in this graph. Let's turn on fast equals false, because this is going to let us zoom in on that maximum just to take a look at it. Oh, isn't that nice? Let's see. I want to zoom select, so I'm going to go along like, yeah, just like that. Yep, that's pretty clear that maximum is right at about 1. Let's change our step size. Let's get 10 times the number of data points. This will take slightly longer to run. Oh, you can see the electric field growing. That's awesome. Here you can see the graph animating. Okay, so let's zoom in on the peak here. There we go. Yep, that maximum is pretty clear at 1. Awesome. So, like I said, this is one of my favorites. Getting this maximum out is so cool. Thank you for letting me share this with you. I will see you next time. Bye-bye.